Chapter 7, the quantum mechanical model of the atom. So until the beginning of the 20th century, it was believed that all physical phenomena were deterministic, meaning that if you understand the present condition of an object, that will help you to predict its future condition. But scientists, mostly physicists, were working on subatomic particles, and they found that the present condition for a particle smaller than an atom does not determine the future condition. This is very different from what we can observe in the macroscopic world, the world that we can see with our eyes. This doesn't happen. What this means is if you shoot an electron down a path, measure where it lands, and then shoot a second electron down the same path in exactly the same way, it's not going to go to the same place. That doesn't work with baseballs. You need a pitching machine, you get it in there, and the ball goes the same place every time, right? That doesn't happen with electrons. That's disturbing. This will be a disturbing chapter, I'm sorry. So we call this the absolutely small world, or the quantum world of the electron. These are particles that are so small that regular physics doesn't apply. So they behave very differently from the large world or the macroscopic world that we can see. So absolutely small particles like electrons and other particles in that size range, when they are unobserved, can actually be in two different states, not geographical states like California and Nevada, but two different states at the same time. So an unobserved radioactive nucleus can be simultaneously emitting a particle and not emitting a particle. Does that seem like it's just not possible? Yeah. Okay, so the scientists that were discovering this had a hard time with it. So just expect that you are not going to completely understand this, because I don't think anybody completely understands this, okay? So electrons are incredibly small. I mean, we've talked about how small atoms are. Electrons are even smaller than atoms. So a single speck of dust, little teeny tiny particle of dust floating in the air, has more electrons in it than the number of people who have ever lived on this planet. In all of history, one dust particle has more electrons in it than all the people who have ever lived on the planet. That's a lot of electrons in a teeny tiny particle, right? This is blow the students' minds day. Too early for that. Pardon me?
What are the main elements that?
Well, dust could be lots of different things. Dust comes from like ceiling tiles. It can be dead skin flakes. And I mean, it's just random stuff, right?
Everything?
Pardon me?
It's a mixture of a little bit of everything.
Yeah, it's just little teeny tiny particles of stuff, right? That they're small enough that they can float around. I look at the dust that accumulates on the counter in my bathroom, and I'm like, where the heck does all this come from, right? I mean, dust, yeah. So electrons behave very differently than what visible objects do. And it's important to understand what electrons are doing because the behavior of the electrons affects the behavior of the atoms. The behavior of the atoms affects the behavior of the macroscopic objects. So we cannot directly observe electrons. I think I showed you the pictures, the scanning, tunneling, microscopy images of atoms, right? That's high tech, and we've just got these fuzzy, distorted pictures of atoms. Electrons are much, much smaller than that. We cannot see them or observe them directly. The other problem is the electron is so small that if you observe its behavior, it changes its behavior. Even shining a light on an electron changes what it does, because it can exist in two states at the same time if it's unobserved. When it's observed, it has to choose one state or the other. So Have you heard of Schrödinger's cat? Some of you have. Okay, so Schrödinger's cat was a thought experiment. It did not involve an actual cat. Okay, so don't call PETA or anything. No cats were harmed in this. We're just thinking about cats. So I've got a couple of videos to show you because I think they do a much better job than I could. So let's watch these.
This wouldn't be a YouTube channel without a cat video. So without further ado, Schrödinger's cat. I'm sure you've heard some version of this famous thought experiment. You put a cat in a bunker with some unstable gunpowder that has a 50% chance of blowing up in the next minute and a 50% chance of doing nothing. The gunpowder is Einstein's version. Schrödinger preferred poisonous gas. But whatever. So until we look in the bunker, we don't know whether the cat is dead or alive. And when we do look, it is either dead or alive. So if we repeat the experiment enough times with enough cats and bunkers and gunpowder, we will see that half the time, Kitty survives, and half the time, Kitty goes bye-bye. The quantum mechanical interpretation is that before we look, the cat is in a superposition. It's both dead and alive. And our act of looking forces nature's decision. So our curiosity kills the cat. But what about the cat's perspective? Well, the cat either sees the gunpowder explode or not. So inside the bunker, we actually have these two possibilities. The powder explodes and the cat sees it explode, or the powder doesn't explode and the cat doesn't see it explode. There's no option, the powder explodes and the cat doesn't see it explode. So the cat's reality becomes entangled with the outcome of the experiment. And it's our observation of the experiment that forces nature to collapse to one option or the other. But we're like the cat too. Either the cat dies and we see it dead, or the cat lives and we see it alive. So who's observing us to force nature to collapse to one reality? Or do both possibilities happen in parallel within a larger multiverse? This collapsing to one reality problem is one of the biggest unanswered questions in quantum physics. So for Kitty's sake, can I have answer, please?
So that's from a channel called Minute Physics, which they've got a lot of really cool stuff. Let me find my other video. This is a great channel also.
Hello and welcome to I Don't Think That Means What You Think It Means, where we look at bits of scientific theory that have wiggled their way into popular culture and have taken on a life of their own. Today we're talking about Schrödinger's cat, a famous thought experiment devised by the Austrian physicist Erwin Schrödinger, who helped piece physics back together after Einstein and his crew blew a giant frickin' hole in it back in the early 20th century. It's hard to overstate how much of a giant crap circus the 1920s were for physicists. Until then, everything had pretty much just been good old-fashioned Newtonian physics, where you could observe objects moving and predict how they react to various forces. But then along comes all this new research into subatomic particles that shows that they don't act predictably at all. In fact, sometimes stuff seems to be two different things at once, like an electron and a beam might act like a particle sometimes and like a wave at other times. And to make things even more the more you try to observe and measure these particles, the less naturally they behave. My friends, I shall now introduce you to one of the biggest mind flogs of quantum mechanics. It's called superposition. The idea that a particle can exist in all of its theoretically possible states at the same time. So Schrödinger came up with this thought experiment to help everybody understand it. Say you have a cat, and you put the cat into a steel chamber for an hour with a vial of deadly gas, a Geiger counter, a hammer, and a tiny bit of something radioactive. Bear with me here. I'll say that there's a 50-50 chance that one of the radioatoms is going to decay and release some radiation within that hour. If one of the atoms decays, the Geiger counter is going to trigger the hammer, shattering the vial of poisonous gas. Really, Schrödinger? This is not the best way to get people behind the idea of funding the sciences. So, there's a 50% chance that at the end of the hour, that vial has been broken and the cat is dead. And an equally good chance that the vial hasn't been broken and the cat's just kicking it, wondering what's for supper. But what's actually happening in the box? According to quantum mechanics, any one of those radioactive atoms would be in a superposition of being both decayed and not decayed at the same time. That's how quantum objects act. So then, that decayed atom will have both killed and not killed the cat, right? Well, that's the logical conclusion, but a cat cat isn't a quantum object. A cat is a big, normal thing that obeys nice, old-fashioned Newtonian laws. So it, just like every other cat in history, is either alive or dead. Schrödinger's point, at least one of them, is that the two objects are subject to two separate sets of laws that can't be reconciled. In order to know whether the atom has decayed or not, and whether the cat is dead or not, you have to open the box and see. But in quantum mechanics, the state of superposition can't be observed. So when the evil mad scientist finally opens the chamber to observe, the superposition collapses and the outcome is ensured. Today, Schrödinger's cat is often talked about as some kind of undead zombie cat, or discussed as if the cat is actually both alive and dead in the box. But Schrödinger's point wasn't to prove that you can make a cat be both alive and dead, but instead to prove that the quantum world doesn't mesh together well with the, like normal world. And alternatively, the point is that the universe is pretty frickin' weird. There are other interpretations of quantum mechanics that might resolve the paradox, but none of them are particularly easy to test. My favorite, of course, is the many worlds interpretation that states that at the end of the experiment, and at the end of every superposition, new alternate universes are created. In this case, one in which the cat is alive, and one in which the cat's dead. And to be clear, I don't like this interpretation because I think it's the most likely one. I like it because I think it's such an excellent plot device for science fiction novels. If you have any questions, and I'm sure you do, ask them in the comments below, and I'll, do my best. Also, if you have an idea, or I don't think that means what you think it means, please let us know about that too.
So this guy also has a great YouTube channel where he explains a lot of science things. So I recommend checking those out.
This wouldn't be a
Yeah, I already did that one. Okay. So, any questions, comments about Schrödinger's cat? It's a cat, yeah. I like cats. Got 2 of them at home. So the idea here is that obviously a cat can't be dead and alive, right? It has to be one thing or the other. That's how things that we can see behave. Quantumly small objects, the absolutely small, like electrons, do not behave that way. An electron can be both a wave and a particle at the same time. If you observe it in some way, then you force it to become one or the other. This is hard to get your mind around. And so if you're bothered by that, let's look at a couple of quotes. So Niels Bohr, who was one of the scientists that worked on this, said, "Anyone who is not shocked by quantum mechanics has not understood it." This was just like, what the heck kind of stuff for these famous scientists. Okay, these guys devoted their life to studying this stuff. So here's Schrödinger. Schrödinger wrote, "I don't like it," referring to quantum mechanics, "and I'm sorry I ever had anything to do with it." Right? That's the thing about science. You investigate something, and sometimes you don't like what you find out. Can you just pretend it doesn't exist? Well, you could, but you really can't, because it does. Albert Einstein, you guys have heard of him, right? So Albert Einstein tried unsuccessfully to disprove quantum mechanics. He kept trying until he died. He didn't like it either. He said, God doesn't play dice with the universe. This is a very disturbing, hard to understand idea, but we need to try. Quantum mechanics explains how electrons exist and how they behave in atoms. It helps us to understand and predict the properties of atoms that are directly related to what the electrons are doing. So, why are some elements metals and others are nonmetals? Quantum mechanics explains this. Why do some elements gain 2 electrons or 1 electron? I'm not even reading here. Why do some elements gain 1 electron when they form an anion and others gain 2? So fluorine gains 1 electron, makes a -1 ion. Oxygen gains 2. Why? Why do they do that? Why are some elements really reactive? Like hydrogen gas, very flammable. Helium, Not at all. Helium doesn't even make any compounds. They're very similar. What's the difference? Why do they behave so differently? Quantum mechanics understands this, explains this. And there's a lot of other periodic properties that we see. And quantum mechanics explains all this.